Alright, so this Unit 5 study guide is helping us prepare for the Unit 5 test. You'll be watching this video and completing some practice problems along with doing the Unit 5 study guide Delta Math because when I asked everyone how they wanted to review, this is what they said they thought would work best, some Delta Math informative combination. So I'll be doing some examples, then for questions that aren't in Delta Math, you'll have some practice problems on this page and you can use formative to check your answers for those problems. So, if you finish today, I would recommend keeping it and turning it in on test day, since test day is when it's due. That way you can have it to study with over the weekend. So, function operations is the first place that we'll start. So when we have functions, we can add them, subtract them, multiply them, and divide them. And then we can also compose those functions, so putting one inside of another. So if the first thing we're asked to do is to add f of g of x, I'm just going to take both my f and g functions, write them down. And I use parentheses to organize so that I know that I've put everything in there for each function. But the parentheses don't really change anything. So then I want to combine like terms, 8x and a 12x, which is 20x. And then 2 and negative 4, which is negative 2. So I don't need to worry about factoring or anything like that. I can leave it just like that for adding two functions together. I can also subtract two functions. And when we subtract two functions, the order does matter. So that means that I need to make sure, since it says f minus g, that the f function comes first, and then I'm subtracting the g function from that. So parentheses here are also really important because we have to distribute the negative that's inside the parentheses or outside the parentheses to everything that's inside the parentheses. So my first parentheses doesn't change at all. The first function stays the same. And then I distribute the negative to everything after that. So negative 1, because we can think about it as a negative 1, times 12x would be negative 12x. And negative 1 times negative 4 would be plus 4. Again, we're going to combine like terms. So 8x and negative 12x is negative 4x. And then 2 plus 4 would be 6. Okay, so order does matter when it comes to subtraction. Okay. Now we can do multiplication. So when we have two functions written right next to each other like this, f and g, we know that means we're multiplying them together. So I'm going to go ahead and write them down. And since we have a binomial times a binomial, or two terms times two other terms, we need to make sure to multiply this using a box or FOIL. So I'm going to do a box here, setting it up. And then to get what's in each square of this box, we are going to multiply them together. So 8 times 12 is going to be 96, and we have x times x, so that's x squared. 12x times 2, 24x, 8x times negative 4, negative 32x, and 2 times negative 4, negative 8. So I need to combine the like terms. So I see I have two x terms here. So I have 96, x squared, 24 minus 32 is going to give us a negative 8x, and then minus 8. If you FOILed it, you also would have gotten the same four terms in the squares, and then would still combine like terms. So the last of our basic operations is f of g of x. like divided by. So when we're dividing a function, again, order does matter, the one that we're putting on top. So sometimes we can think about it like this, like f of x over g of x. So here, I'm going to write our f of x function on top, g of x function on the bottom. We're not always going to be able to simplify a fraction like this, but we want to check and see if we can. So if I look at the numbers 2, 8, 12, and 4, they can actually all be divided by 2. So I'm going to divide each of those numbers by 2 to get my most simple form. So 8 divided by 2 is 4, 2 divided by 2 is 1, 12 divided by 2 is 6, negative 4 divided by 2 is negative 2. Just forgot my x. Okay, and then the one thing we do need to think about with a fraction is we're going to have a domain restriction. So this means a specific x value where x cannot be, because it means that we would have an undefined function. It just doesn't work. So for us, we know that that means the denominator cannot be set or cannot equal 0. So to find out what that number is, if we can't easily tell, so we do 6x minus 2 equals 0. And then we just solve for x. So I'm going to add 2 to both sides and then divide by 6. We know that 6 and 2 can both be divided by 2, so that simplifies to 1/3. So we would say that this function is 4x plus 1 over 6x minus 2, but x cannot equal 1/3. Okay? Because that's our domain restriction. Okay, so those are our 4 kind of basic functions that we're used to using, but we did learn another one. So we learned a composition of function. So when we have f of g of x, or you can see it this way, f of g of x, right? Either way. So this means that I'm going to take my f function, and inside of my f function, I'm going to write my g function. Okay, so that means wherever I see an x in my f function, I am going to leave a big open space. And wherever that open space is, or that previous x was, that's where I'm going to put the g function, or the inside function. So 2x minus 4. Okay, after we put one function into the other, I can just distribute. So I'm going to distribute the 8 only to the 12x and the minus 4x. So 8 times 12x would be 96x. 8 times negative 4, negative 32, and then plus 2. We combine any like terms, we get 96x minus 30. You can also compose the other way. Remember, it doesn't matter which letter tells us is which, so we could have the g function come first and then be putting f into the g function. So again, this is a review on our 6 or 5 function operations. And there weren't great Delta Math questions on this, so you'll see your practice problems for this are below. There are 6 practice problems here, and then after you complete those 6 practice problems, you can check your answers in formative using the question numbers to see if you got them right or not. And then there's also one section in Delta Math for composition to get a little more composition practice. So you can use this space right here to show your work for that section. So go ahead and pause the video so that you can complete those 6 practice problems and then do the Delta Math. And then when you're done and ready, you can come back and we are going to go over the inverse review. All right, so hopefully you feel good about inverses at this point. If not, good about composition of functions at this point. If not, you have both of the practice worksheets that we've done in class. You should have both of those back, and those are great practice problems to work through also. So now we're going to take a look at inverses. So we had 4 easy steps, quick steps that we were using to solve inverses, and the only math part is solving each equation. So whenever we are talking about inverses, we want to think switch x and y. This is true whether the question is talking about a graph or a table or an equation. Just remembering to switch x and y is the basics of any inverse problem. So I don't see a y in question 1, so I have to go ahead and replace f of x with y, because we know that f of x or g of x or h of x is always the same as y. And then now we're going to switch x and y. So x equals 15y plus 4. Then we're going to solve for y. So subtract 4 from both sides. X minus 4 equals 15y. And then divide both sides by 15. It cancels out on the left or on the right hand side. And then remember, on the left hand side we want to write it in slope-intercept form if possible. So we just break it up like that. But when we write our inverses, we want to make sure that we're putting it back in inverse form. An inverse form is where we have the f and then the little -1 equals x. So that is what our inverse form is going to look like. That -1 is not an exponent. It's just a notation form for when we talk about inverses. All right. So we have another inverse problem. So this one, again, we're going to start by putting in a y value since we don't see one. Okay. Now we're going to switch the x and the y. And now I need to solve for y. So I'm going to subtract 1 from both sides.
Here's the contact info for Myra Jack.
And then we need to get the rid of the squares. The way we get rid of a square is by square rooting both sides. Okay, and then again we get the y by itself by adding 3 to both sides. But when we do this, we have to be sure to add the 3 outside of the radical because it's not a part of the radical. It's not a like term with the 1. So after we get this all set up, we get y by itself. The last thing we have to do is switch that final answer to include the inverse. Excuse me. Right. So now we have our inverse function. Okay. So a couple more things about inverses that I want you to remember. The first is that if we need to verify an inverse, we have 2 conditions that we need to meet. So if f of g of x. So when we compose it one way, if it equals x. And then if we compose it another way, and it also equals x, then the functions are inverses. So those are the two conditions that we have to meet. If we compose them and one of them does not equal x, we don't even need to try the other one because we know that it's not a function. If you're given a question with a table or a graph asking for the inverse, remember that we just want to switch the x and y value. So if you're given a graph, you can get points from a graph, and then you switch the x and y. It's kind of the main theme of inverses is switching x and y. Again, there are a couple practice problems down here, 7, 8, and 9. And then after you can complete those and check those informative, there are 2 sections on inverting linear functions and evaluating functions and inverses from tables on Delta Math. So there's some space here for you to show your work on those. You can use a separate sheet of paper if you need to. But go ahead and pause the video, complete the inverse questions, and then come back. We have 2 more sections that we need to review for Unit 5. So hopefully you feel good about function operations and inverses at this point. Now we're going to go ahead and look at some radicals question. This is what we started Unit 5 with, so it might feel like a little bit long ago, but I think it'll come back quickly. So when we solve radicals, we always need to make sure to isolate the radical before we do anything else. So to isolate this radical, I'm going to subtract 4 from both sides. I get square root of x minus 3 equals -1. To get rid of the square root, I'm going to square both sides because those are inverse operations. I have x minus 3 equals 1. To get x by itself, I add 3 to both sides. And I get x equals 4. One thing we always want to do with radical problems is we want to check and make sure that we have a solution that works. So I'm going to write my check stage here. And that means that we're plugging 4 back into the x of the original problem, and we're going to simplify to see if we get the same number on both sides. So here, I'm going to have 4 minus 3 plus 4 equals 3. So we always want to use the very original problem before we do any solving. That's going to help us have the best check and to make sure that we didn't do any algebra steps wrong that could mess us up later on. So 4 minus 3, we want the square root of 1, plus 4 equals 3. The square root of 1 is 1, which I can tell here that the square root of, 1 plus 4 is not 3. So when we go to plug back in, x does not work. So instead of just leaving it blank, we would say that this is no solution. We actually call that -1 an extraneous, that 4 an extraneous solution, which means it's a solution that looks like it works, but when we plug it back in, it's not actually in the domain of the original function. So let's take a look at number 2. So on number 2, our square root is already isolated here. So I'm going to go ahead and square both sides of the equation. The square root and square cancel out on the left side. So I have 4n plus 8. And then on the right side, since I have n plus 3 times n plus 3, I know that to multiply that, I'm going to need to use a little box. So I'm going to come over to the side and create a box. So n plus 3 on one side, n plus 3 on the other. N times n is n squared. 3 times n, 3n. N times 3, 3n. 3 times 3 is 9. I see I have two like terms here in the middle. So I have n squared plus 6n plus 9. And then when we have a quadratic, so something with a square like this, instead of getting all of the variables on one side, we try to get everything on one side of the equation in order to be able to factor it, because factoring is how we solve quadratics. So I'm going to go ahead and subtract 4n from both sides. And then subtract 8. Now I have my quadratic equal to 0. And I need to factor. So if you use the box method of factoring, let's go ahead and create a box again. So n squared and then 1. So I'm looking for two numbers that multiply to 1 and add to 2. And it's actually, we only have one combination because the only numbers that multiply to 1 are 1 and 1. So we have 1n and 1n. So that means our outside is going to be n plus 1, n plus 1. So if we write out those factors equal to 0, now to find out what each parentheses is, which in this case they're going to be the same, we take each one and we set it equal to 0. So here we have n plus 1 equals 0. And I'm going to subtract 1 from both sides to find what n is. So right now, we think n equals -1. But before we confidently say that's our answer, we want to check. So we were a little cramped for space here. But I'm going to go back to the original problem, and everywhere I see an n, I'm going to replace it with -1. So 4 times -1 is -4. -4 plus 8 would be 4. And then on the right side, we have 2. And we can see that the square root of 4 is 2. So that one's good. So this, -1, is a solution. It is possible with problems like these that one answer would be a solution and the other one would not. So you definitely want to plug in both of them to see which one is and which one's not. If you plug them in and you see that both of them are not, then there would be a no solution problem like we saw in example 1. So that's kind of a crash course on solving radicals. But we do want to do a little review on simplifying radicals. So here, that's what we're going to do in 3, 4, and 5. So when we simplify radicals, we want to be thinking of those perfect square numbers, right? So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. Those are the numbers that we need to successfully simplify. So I'm going to go ahead and if I take the square root of 90 and put it in my calculator, I'm going to get a long decimal. And with all of these, we want to avoid decimals and just simplify in radical form. So I want to think of two numbers that multiply to 90, where 1 is a perfect square. The first one that comes to mind is 9 and 10. So when I take the square root of 9, I get 3. That becomes on the outside. And then square root of 10 stays on the inside. I'm going to do the same thing with 40. Think of two numbers that multiply to 40, where 1 is a perfect square. I think of 4 and 10. So the square root of 4 is 2. So 2 comes on the outside. 10 stays on the inside. And then in order to combine radicals, adding and subtracting, we need the radicand to be the same, so the number underneath the square root. In this case, they are the same, so then I can combine the coefficients that's in front. So 3 minus 2 is just 1. So I would have 1 square root 10, but we don't need that one in front, so we would just say the square root of 10. Okay, we're going to do the same thing here in 4. So if I look at 2 square root of 5, I'm trying to think of two numbers that multiply to 5, where one of them is a perfect square, but the only two numbers that multiply to 5 are 1 and 5, so that one can't simplify. But maybe we can simplify the next one. So two numbers that multiply to 12 are, where one's a perfect square, are 4 and 3. So I'm going to go ahead and bring the 2 square root 5 down and then add my plus sign. When I take the square root of 4, it's 2. And then square root 3. And then again, two numbers that multiply to 27, where one is a perfect square. We have 9 and 3. Square root of 9 is 3, so 3 comes on the outside. And then the other 3 stays on the inside. So when we look for like terms, these last two are like terms. So the 2 square root 5 would stay the same. And then 2 plus 3 would give us 5 square root 3. It's okay to leave them as two separate radicals because we cannot combine them unless the radicands are the same. So now looking at our last one, this one has multiplication. So when we multiply radicals, we want to multiply coefficient times coefficient and radicand by radicand. So I still have to distribute here. So if I multiply 2 is technically a coefficient since there's nothing under the radicand. So 5 times 2 is 10, square root of 5. Then 5 times 5 on the outside is 25. And 6 times 5 is 30. We know we can't simplify the 5 at all. But let's see if there are two numbers that multiply to 30 where one of them is a perfect square. So I'm going to try 4. So 30 divided by 4 doesn't work. 30 divided by 9 doesn't work. 30 divided by 16 doesn't work. So after that, we see that our numbers start to get really big, really long decimals. So there's actually no way that I can simplify this one because 30 doesn't simplify. So after I multiply, I can leave it just like that. But we always want to make sure that our radicals are in the most simple form. Okay, so crash course on adding and multiplying radicals and subtracting them. So this one we are doing mostly in Delta Math. So there's 3 Delta Math sections: radical equations level 1, radical equations level 2, multiply radical binomials, adding and subtracting radical expressions, and simplifying radicals. There's just 1 or 2 questions for each of those sections, so don't get overwhelmed by the number that there is, but use the space here to show your work. So go ahead and pause the video now, do those radical questions, and then come back for our very last section. So this last section is actually the very first section that we learned in the radicals unit, but we've done transformations and domain and range before, so we're just applying them to a new type of function. So the first thing I want to talk about are transformations. So I've written out here a basic radical function, and so we're going to see what different things do to change, shift, translate that function. So first, if we're looking at this negative sign that's in front, that negative is going to reflect our graph over the x-axis. Okay, so that means it's going to flip it. If it was going up and to the right. Now it's going to be going down and to the right. And then when we have an h, if we have a minus h, that's going to move our function. It's going to move it right. So it's kind of doing the opposite. So it's going to move to the right h units. If it's a plus, then it's going to move it to the left h units. And then our k is what moves it up and down. So if we have a plus k, it's going to go up. Oops. And if we have a minus k, it's going to go down. Okay, so if we're given just a generic function, okay, so if this is the function we're given and it said to state the transformations, then I'm just going to look for the numbers. So you see I have a minus 3 here and a plus 7 here. And where they are is going to determine how I'm shifting this graph. So minus 3, it's in the position of minus h, so it's going to go right 3 units. And then that plus 7 is going to move it up 7 units. Okay, and that's all it's asking. If you aren't sure, you have a hard time remembering these rules, another trick is that you can always graph it in Desmos and look for how it moves from the point 0, 0. So you'll see there's like a starting point on the radical, and wherever that point moves, you can use that to help see what your transformations are. And then the final thing we need to look at is domain and range. So a refresher that domain is talking about the x's and range is talking about the y's. So remember, this is talking about the possible x's and the possible y's, or where we see x's and y's on our graph. So first, let's start with domain. So if I go to kind of the end point of my radical, it's right here at 1, 3 in this first picture. So the smallest x value that I see on this graph is 1. I use a bracket because there's a closed circle there. If there was an open circle, I would use a parentheses. And then I look to the right of that 1, of the x coordinate of 1, and I see that there's an arrow pointing to the right. So it's going to go on forever and ever. So my domain would be 1 to infinity. We do have to remember that every time that we have an infinity sign, we put a parentheses next to it, not a bracket. Okay. And then we're going to think about it the same way, but for range. So here I see that my lowest y value is 3. So I'm going to start at 3 with a bracket. And that my y's are going to continue increasing this entire time because the entirety of my line is above that y value of 3. So my range is going to be from 3 to infinity. Again, using that parentheses next to the infinity sign. Okay. One more example here. We see this one's been flipped a little bit. So we're still given that starting point of 2, 0. So looking at the domain, the smallest x value I see is 2. And then it goes on and on to the right-hand side. So my domain would be 2 to infinity. My range, if I look at it, 0 is like the biggest y value because all of my line is below 0. So I'm actually going to start my range at negative infinity and have it go to 0 because everything is below 0. I put the negative infinity first because I want to make sure that my domain and range read in order from least to greatest. So see our domain and range on there. So for this one, there's no Delta Math questions. So at this point, you should be done with all of your Delta Math sections. There's just like 2 different questions here for you to practice selecting your transformations and then stating the domain and range. Both of these you can check in formative when you finish. And then the last thing I don't want you to forget is there's the radicals review sheet. So that had a lot of additional practice questions for the things that we learned at the very beginning of the quarter, the things that you watched a lot of videos on while I wasn't here. So I am saying that radicals review sheet is due on test day, but in reality, it's extra credit. So if you're continuing to watch this video, you know that, and you can choose to decide whether or not you're going to complete that. But the radicals review sheet, make sure to show your work, because I will be picky on that, but it is due on test day. So make sure to spend additional time on any questions that you have. There's all of the review videos that are posted in Teams in addition to this. Make sure to ask me if you have any questions before you leave today.